I want to thank you all for joining us here today at the Python Web Conference. I introduced myself earlier, but I'll do it again. And I brought along a teammate with me. So who are these guys sitting in front of you? My name is Calvin Hendryx-Parker, and I am CTO and co-founder of 6 Feet Up, but also co-organizer of IndyPy. And I brought along an interactive audience. You may have noticed on the schedule it was supposed to be a solo act. I decided that was going to be a little bit boring. So I thought that it'd be really fun to bring along Kim Nguyen. And so I'll let Kim give a quick little introduction.
I work at 6 Feet Up, and I'm a project manager here. And I'm very curious to know a lot more about how Calvin's going to introduce Plone on AWS.
Funny, me too.
Yeah.
Yeah. So I guess we'll try and see if we can do that. We'll just go ahead and get started. A lot of this talk is based on some work we've done with a couple universities, and even our own 6 Feet Up site runs on AWS. So if there are questions for it, we are watching the Cloud Native channel in Slack, and someplace I assume the Q&A would show up in Zoom if you use that feature. But I think Slack's probably best. We're both on Slack right now, so we can actually answer questions. If you haven't seen a talk I've done in the past, I did a talk was titled The Rules of DevOps Club. So if you guys have seen Fight Club, you'll understand the rules of Fight Club. First rule of Fight Club is you don't talk about Fight Club. First rule of DevOps Club is you don't log into servers. And for us, that gets down to when you create a server and you're running Plone, and kind of the historic, because Plone's been around pre-cloud, so everyone who ran Plone in the past always ran Plone this way on a monolithic server. A lot of times, I'd say 98, 99% of the time, those servers are beautiful, unique snowflakes. Exactly. The admins will, acquire a piece of hardware, install an operating system, start installing random packages, attempt to get Plone running, realize something is missing, start installing a couple more packages, realize they've missed a couple more things. Then they'll install some monitoring packages, some other things to watch this thing, another thing to do some document conversion. They may have another little special tool that integrates with some legacy third-party bit. And by the time that is all said and done, which usually goes over the course of many years, you end up with a beautiful and unique snowflake, which beautiful and unique snowflakes are definitely not reproducible. And a little bit of trivia for you is the chances of a snowflake being exactly alike is 1 in 1 million trillion. That's 1 followed by 18 zeros. That's a big number, 18 zeros. So the chances of you getting your server to look exactly the same twice by hand is relatively similar to those same odds.
I got a story about that.
Yeah?
Well, in 2016, I helped put together the 2016 Plone conference site. And that was, we started off with an Ansible playbook. So we were trying to fit with the idea of reproducibility. And, then people would talk about, oh, I found a bug. So someone would go in and fix the bug on the server and then update the playbook in retroactively. But over time, we got to the point where nobody should run that playbook again, because that server its state is not reflected in the playbook. So it's very scary.
It was a close approximation was in the playbook, but it wouldn't have actually done it.
Yeah.
Right.
So yeah, snowflakes are dangerous.
Snowflakes are very dangerous. So these beautiful, unique servers, they're kind of like pets, right? We love our pets. I'm a cat person personally, so I figured I better put some cat pictures into our presentation. I have a cat named Macintosh. I have a cat named Mighty. We care for them. We give them special cute names. You may have noticed this had happened in the past that servers would have especially cute names.
Well, yeah.
I once worked at a company where they had a rack of servers literally called the spice rack. And each server was like basil, thyme, cardamom. Good luck spelling that, getting into it. So they gave them cute names. You cared for them. If your server or your pet got sick, you would take it to the vet or take it to your system administrator. They would attempt to, as much as possible, they would attempt to resuscitate and bring it back to good health. That's how you care for your pets, right? And we would give them cute names, and we cared for them like that. But really, in actuality, we need to treat our servers and our infrastructure a little bit more like cattle. And I hope there's no vegans in the room that'll be terribly offended by this presentation. But with cattle, you can see right there on the slide, they have a number. They don't typically have names unless you're just kind of weird like that as a cattle farmer. But you if they get sick or they get kind of, you take them out of the herd, you may put them into a separate place and not actually utilize them as part of your normal operation until if they come back to health, great. If not, they can be replaced by another cattle, or a server just has a name, a number. It's not actually any handcrafted bare metal server underneath there where some admin has, done some kind of bespoke deployment of code and software to that server. We can now just take that server out of the load balancer, out of our auto scaling groups, or out of wherever we're using it, and replace it by another one instantly without missing a beat. And that's kind of this server cattle versus pets argument that you hear a lot of times when people talk about cloud computing and run into the cloud. So for us, Plone being kind of pre-cloud, it's not necessarily a cloud native first application. It was developed in a time before DevOps was probably even a word. There were developers and there were operations people, and they would have Nerf gun fights in the offices, but that was kind of the extent of their interactions. Wouldn't you say that would be kind of correct?
Definitely. I mean, Plone predates that cloud thing, although there are Amazon images for Plone,
right.
Plone deployments.
But even before Amazon existed, there was Plone.
Oh, well before.
Absolutely. So how do we translate this application that was originally meant to be run in the monolithic server into a more cloud native stance where we can now not have cutely named servers that we care for very, very carefully? So I want to tell a quick story about a little more like going from the closet to the cloud. One of our customers, College of Engineering Notre Dame, they've been hosting their main Plone website on a single server. I think is literally hosted in a closet on campus. Now I've heard stories of like servers on campuses being walled into, like drywalled into walls and still running, and they have to like trace down Ethernet cables to find them. I think it's pretty close to that situation because connectivity would get kind of iffy sometimes. There's obviously no redundancy to it. It's tricky, right? Because you kind of got to manage this one server. It's going to have a cute name probably. But now they've got this single server. How do we go from this single monolithic server up into a more cloud native stance in our infrastructure wise? Now what happened was in 2016, university wide, they made a decision that they were going to go AWS campus wide. So at this point, the College of Engineering had no other choice. They had to move their application into the cloud. Now, when you move a single monolithic application into the cloud, you want to make sure you're taking advantage of all the various cloud architecture pieces that are available to you. There's no reason to lift and shift. I mean, you may hear that a lot. I think a lot of people, a lot of ops people, a lot of enterprise software salesy people will use that term lift and shift. I'm surprised they don't have a 3-letter acronym for it, like TCO or TLA. There's lots of those in this industry. But with lift and shift, you end up building something that is obviously still single point of failure, is going to be more expensive to run because you're going to need to have a larger cloud instance to run all the things on that single monolithic database or that single monolithic application, because you've not split it up into other little components that can be scaled appropriately for their needs. So we look at this like single monolithic server. This is what they were currently running in their closet at the university campus. So there's basically a web stack of an Nginx front end, which handled things like the rewriting and for the proxying back to the Varnish cache. The Varnish cache is handling all the HTTP acceleration, so allowing the JavaScript, CSS, certain images, certain pages, depending on what your rules are, to be cached and not delivered by Plone. HA proxy was in the mix, so we could load balance across the 4 Plone instances that were running with a Zio server storage backend. So if any one of those pieces failed, they will, the whole server will basically stop serving the site. And so you have no other option other than to go in, probably by hand, try and fix this thing and bring it back to good health.
And definitely here, if you've got a single server, you have to, if you're expecting a lot of data, a lot of storage, you're going to have a big server.
That's true,
for all the storage. And then if you've got 4 Plone instances, each one of those CPU can hit pretty high levels.
And memory usage. Plone's has been notorious in the past for memory usage. Although on the new Guillotina and with the Volto, how is that on memory? It's a little sidetrack.
Very slim.
Very slim.
I'm hearing really good things about how fast and slim it can be.
I'm excited about that. Your talk on Volto was awesome. So if you haven't seen his talk, go check out his talk. It'll be on recording. Will be up soon. And then you may ask, like, why Nginx, Varnish, and HA Proxy, all three of those tools can technically do load balancing. And I'll get into some of the architecture stuff along the way and like why some of these decisions were made. But I definitely believe in the Unix philosophy when it comes to how you architect and lay out the applications that will handle your application. You should pick the one right tool that kind of does the one task very, really well. And that's been the Unix philosophy for all of its tools, like, ls just lists files. Nginx is an excellent, like, small Swiss Army knife of a web server. It does a great job of like rewriting URLs, doing redirects, rewrite maps. So I put it up front for that reason.
SSL also.
And SSL termination. So it's very lightweight for all those things. Varnish is a web cache and should do nothing but web caching. All three of these tools are actually capable of doing load balancing to some level, but not all of them do it as well as, for example, HA Proxy. HA Proxy is kind of the granddaddy of web proxies and can do load balancing with like sessions and statefulness, health checks, and those are a lot trickier to do in Varnish. So I could have eliminated pieces of this stack and made it simpler, but I don't think we would have had easier time of managing the whole stack of servers. So if we want to take this single monolithic server and turn it into a more, what looks like a cloud native application, we're going to have to break this up a little bit. We're going to try and use, since this talk is very specific about Amazon Web Services, we're going to have to try and use specific Amazon Web Services along the way so that we can take advantage of not having to manage those servers and services, and I'll talk about those as we go. So here's a kind of a view of what a cloud optimized version of this will be. And we'll run through, I'll go into the AWS control console and we can actually run through some of these pieces and I can kind of go over that. And I hope you'll keep me honest about why we made certain choices and
Yep.
where the advantages and benefits are. So if we talk about the front end, we have replaced out, there's no more Varnish and there's no more Nginx in this specific use case. We've replaced that with just HA Proxy only. So if you'll see the application servers here, I don't know if I can see my mouse. Yep, oh, look at that, nice big pointer on there. The application servers, these are the EC2 virtual machines, the thing you would consider to be your standard typical, uh-oh, we've lost our camera.
Oh.
I need a battery change.
Oh.
Here, I'll get it.
Scoot back here.
No.
I think we're back on.
Ah, we're back. Sorry about that. So if we want to talk about this like cloud optimized, our standard, like what we consider to be a server, are these AZ1, AZ2, EC2 instances are there. But you notice we've taken out a lot of the components and moved them away from the application server itself.
So let me stop you.
Yes.
EC2 and AZ.
So AZs in this case stand for availability zones. We're going to try and achieve a higher level of availability for our application itself by splitting the application across multiple availability zones inside of one single AWS region. So Amazon has, was it 20 plus regions around the globe. Each region has 3 or more availability zones that are separate data centers inside that region, separated by some minimum number of miles.
Right.
So that if a storm came through one availability or region, hopefully it doesn't take out all 3 availability zones. For example, US East 1 has like 6, 7 availability zones available for you to use and deploy your applications to. So it's important when you actually set this up, because if you get a default AWS install and you put everything inside of just one AZ, you're still susceptible to Amazon having outages, which they do. They're not completely devoid of.
I remember a big one about 4 or 5 years ago.
Mm-hmm. So we do want to take that into consideration when we're going to this more cloud optimized layout, is using multiple availability zones. And so those are EC2, which are just VMs, virtual machines running, in our case, FreeBSD, but you can run Linux, whatever you want to run your Plone application on. These are our cattle in the diagram here, really. They don't store anything we care about. There's no data on these application servers themselves. The data for the application is going to be stored off in Amazon specific services. So for the backend, like ZODB, so those of you who are using Plone, you should be familiar with the fact that Plone has the ZODB as its like backing data store That's where your content goes, other than things like large files. Those large files go into blob storage. And for blob storage, we're going to put that data into EFS, which is the Elastic File System. It is a hosted NFS v4 file system that you can mount up across multiple servers simultaneously. You may ask, well, why not use S3 for this? Because object store seems like it'd make a lot of sense. It's a lot cheaper. The problem with S3 is you can't, unless you're using some kind of other commercial tool on top of S3. Typically, it doesn't present itself as like a POSIX file system that you could just mount up to any number of servers. Where with EFS, you can have that mounted on any number of servers. You could have 1,000 servers mount up your blob storage simultaneously and all read and write to those blobs. So our data level is basically from here down, we store our data in EFS and RDS, so Amazon Managed Services. We aren't responsible for servers. We aren't responsible for operating systems. We aren't responsible for uptime of those things. That is underneath like Amazon's level of responsibility for the infrastructure.
So here, RDS is the database storage? RDS?
Correct. Yeah.
Right.
So that's the relational database service.
Okay.
Now you may ask, how are we using a relational database with Plone?
Yes.
We typically use rel storage with our application. So in the application layer up here, each of these are just running a single ZOP instance, not a ZO, like you would do in a normal cluster. Like we were showing here, this is using a ZO storage server. Each of these instances were technically not ZOP instances, they were ZO clients to that backend data storage. This is switched around. These have a Postgres connection string, and they just connect to a relational database that now stores the ZO. It's basically a pluggable backend for ZODB. It's still ZODB. We're just not using ZO, but we're connecting to a relational database to store the.
It's the pickles, isn't
it? The pickles, yeah,
Mm-hmm.
Exactly. So you can't go and query that relational database and run some SQL select statement against it and expect to get like content. If you knew what your Python models look like, and if you knew what the indexes were in the ZODB and all that kind of things, you technically could. It's really tricky. It's just lots of integers and pickles and indices, and so it's not a human SQL accessible form other than if you have the application running as an EC2 instance.
So we're replacing the pickles in the data.fs with this RDS.
Exactly, that's correct. There's no data.fs living on any of those servers.
Okay.
So any of these servers can technically fall off the face of the planet. We don't care. The only thing they would have on them, if you aren't shipping your logs off to another place like a CloudWatch or using Datadog or some other external tool, Elastic, Elk, then your logs may be on there, but that would be just mostly useful for troubleshooting or the kind of understanding if there's any issues. But these can come and go. You can spin up new ones, shut them down, start them back up. Doesn't matter. I'm not talking about how we're doing that yet, but we'll get into a little bit of that later. So managed services down here from Amazon for the blob storage and the relational database. And then we basically will snapshot and copy those snapshots of the database and the Elastic file storage, the blob storage, to S3 for backups. What's nice about S3 for backups, it has 11 nines of durability. So you're durability, not availability. Very a good distinction there. But at least we're sure we have the data someplace. We may not be able to access it. Most likely we will, but the data is stored someplace safe. At that point, you can now leverage things like they have cross-region replication available for S3 buckets. So we could actually technically have a DR plan that all it involves is clicking a couple buttons or writing a script to set up the cross-region replication of S3 into some of the regions. So if you're hosting this in US East 1 and then want to, on a disaster, fire it up in US West 1, you could have the data all sitting there in an S3 bucket ready to go. All you do is run your configuration management tools and infrastructure tools to blow out the infrastructure into the spot, restore your data, and you're back online again.
And if you wanted to use some of those tiered storage services, could that be doable too?
Correct. So you probably would want to have them use that infrequent access. So you can actually start reducing costs here by having policies in place on those buckets to take old backups, and if you basically on infrequent access pay when you access them more than you would pay if you're accessing them frequently, like on a normal S3 bucket. So you can start aging out and actually set up life cycles inside the buckets alone without having to have any scripting knowledge. You can set up timeframes for certain like TTLs for certain backups to basically roll off automatically.
Like your monthly backups, your yearly backups could all go to long-term storage.
Exactly. It would like somehow age out into Glacier if you really wanted to keep something that long. So that's the application and where we're storing and serializing all of our data. On the front end, we want to focus on availability and speed of delivery. We've gotten rid of varnish in our infrastructure at this point, and we want to replace it with a CDN. So Amazon has a CDN product they offer called CloudFront. It's a pretty simple product. It has some quirks here and there, which we can talk about. There's definitely quirks in a lot of these things. But with the CloudFront product on the very front end of the site, we now have, it's something like 147 different points of presence around the globe where CloudFront has a entry and exit point for people who access your website to be able to distribute the content. So all the site will be running in US East 1 in this example, but the data could be coming from a more closer point of presence for you as the end user accessing the website.
So I come from the Cloudflare world, and I always thought it was curious that they named it CloudFront here in Amazon, but I think it's the equivalent.
Yeah, it's the exact equivalent. If you are a Cloudflare user, this is the same kind of tool. And CloudFront can be used without using AWS services. Like you could sign up for AWS, use CloudFront only like you would use it in Cloudflare. You set up an origin that is hosted, say in your data center or on your laptop or whatever, wherever your craziness to put that kind of thing. And it can actually host your site. And you get some conveniences if you are using, for example, a load balancer that's an Amazon load balancer, because basically now you have an ability through the console to just pick from a dropdown where the CloudFront's origin is for your site. And the origin is basically, where is the content going to come from when someone requests www.6fit.com? And that request will come to CloudFront all across the globe, depending on where you're at. You'll try and get the closest node to you physically. And then it points back to our Elastic Load Balancer, which is in US East 1. The load balancer, everything below, the ELB and below, are all in one region. And then these are in different availability zones to give us high availability. And CloudFront will be caching pages. In our case, for like the 60 website, we cache more than just JavaScript and CSS. We will also cache into their pages. So if we get mentioned on Hacker News or Slashdot, I'm dating myself by saying that.
Reddit.
Oh, wait, what? That's what the kids use, right?
Yeah. I don't even know how to get there.
So now look at us. So if we did happen to get mentioned on one of those popular sites, more than likely our site would not fall over because I try to get 99% of the site actually hosted out of CloudFront full time. Only when content changes at this application level does it actually invalidate items inside that CloudFront CDN.
Right.
How do we do that, you might ask?
Okay, yes. How do you do that?
If you're familiar with using Plone app caching or CMS caching kind of back in the day, we typically had those targeted toward Varnish or Squid caches. So you could send purge requests, which are basically a special HTTP request to a Varnish cache to say, hey, you can get rid of that page. Next time someone asks for it, it'll ask for a fresh copy from the application servers. CloudFront doesn't speak HTTP except to clients coming and looking for web pages. On the backside, if you want to invalidate something across the 147 points of presence around the globe, you have to speak Amazon's API to them. So we have written an add-on product for Plone. I think it's called collective.cloudfront. You can probably find that on the collective GitHub. And if not, ping me because I'll make sure we get it up there. Because it's an open source product that anybody can use with CloudFront and Plone. So that same type of functionality as Plone app caching. If someone edits a page, a save happens, a workflow transition happens, something gets published, something gets retracted, all those events, the CloudFront product in Plone listens for those and sends API invalidation requests to the CloudFront server on the front.
Slick.
Yeah. And CloudFront's relatively inexpensive. You pay for the bandwidth like anything else in Amazon. You don't have to pay for any kind of storage because it's just going to have a cache of things there. You also do pay for invalidations. So if you have a very active site, you'd have to have a lot of edits before you start paying for those invalidations. I think the first couple thousand are free. So 1,000 invalidations. And invalidations can be batched. So if you really did have a very active site and wanted to batch invalidations, you could provide like globbed paths to a set of pages, and that counts as one invalidation instead of like page.
Okay, so you have to be smart about it.
You have to be smart about it. And typically with Plone, if you, for example, edit a single page, you can invalidate that page, its folder, and any other things you've defined in your policy. For example, if your blog posts show up on the home page, you may, whenever you edit a blog post, invalidate the cache for the home page so that the home page is always fresh and shows the latest blog posts. Those 3 URLs are 3 objects, but it can be 1 invalidation.
Okay.
So you aren't paying like 3 invalidations when you do that 1 invalidation.
Okay. How are we doing for time?
That's a good question. Actually, what time are we supposed to end?
I think we had 45 minutes. We have
Is that right?
15 more minutes.
Do we have 15 more minutes? Is that it? Man, it's going quick. You're such a good co-host. That's probably why, right? Let me make sure we don't go over time because I think I'm in the next thing. Oh yeah, so 11:35. We've got like you said, 20 minutes. 20 minutes.
Okay.
Don't cut me 5 minutes short.
Oh,
all right.
It's good stuff.
It is good stuff. So those are the infrastructure pieces inside of Amazon. But how do we make it repeatable? I mean, we could still do the pets version of these servers. You could log into the AWS console. You can go click, 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 and make these things all happen. Log into the SSH into the servers. Install all the dependencies for Plone.
I love it.
Same thing. Yeah, no, we don't love that. We don't
break my fingers now.
Yeah, I'm going to.
Yeah.
I will ruler.
Yes. I know I'm bad with the playbook, so break my fingers.
Glad I know this about you now. All right, so I'm going to get into how we actually can build this up a little bit, but we basically rely on automation tools like Terraform and Saltstack. So to build up these infrastructure pieces, and I'll talk about the next slide about the network underneath. So I've not even talked about the network here. We really only talked about the application pieces that are running this, but there's a whole set of infrastructure underneath this that you have to get correct as well, because you may want to have your RDS and your EFS in a private subnet that's not accessible to the internet, even if they had access to your public subnet. So you can establish public and private subnets and put all the pieces into the correct subnets and security groups, so you can actually have fine-grained control over the security of the application as you go down the stack.
I think that kind of security with Amazon is really important, because we keep hearing about all these stories about some S3 bucket that was left open. I can't believe people are still doing that.
Right.
So this kind of security is really important to get right. Until Amazon makes it the default.
Right. So speaking of kind of the things that are underneath as far as security, this is actually what the network looks like. We can actually set up different VPCs, which are virtual private clouds, and we want to do an environment, a cloud, virtual private cloud per environment. So we have a production environment, and in our case, I've set up a test VPC as well. They can't necessarily talk to each other. So if someone hacks your test environment, they can't get into the production environment. And if you're following good security practices, typically like access into the production environment uses different credentials than access into your test environment. And you have different people who have access to those things as well, because you don't want your developers just jumping on a prod. You may have heard of people who've done this kind of nefarious activity.
I don't know what you're talking about.
And then we have another VPC, which is our control VPC. So our Terraform and our Saltmaster. So Salt runs in a master and minion. So it has agents running on little servers. It has a master running on a single server, or you can cluster it into highly available. But in our case, to keep things simple, we have a single Saltmaster, and that allows us to build up an environment instantly. Like we can basically run one command, say release a production environment or create a production environment, and it will go create all the VPC subnets, all the NAT gateways, all the things that are kind of under the covers, and then build all the infrastructure on top of that. So the EC2s, the ELBs, the CloudFront distribution. So in one command, we get the whole running stack all at once.
So what's the relationship between Salt and Terraform?
So Salt and Terraform have some overlap. Salt is a configuration management tool. Terraform is as well. For us, we focus Terraform on the infrastructure pieces alone. So if we want to build up an infrastructure like this on Amazon, so all the pieces you see there, plus all the pieces you see here, not necessarily the software that's in the server, but the infrastructure pieces alone. I need an EC2 VM, I need an RDS instance, and I need a database, I need these security groups, I need these private subnets, I need all these pieces. We rely on Terraform for that. Terraform does a really good job of, you model what you want to have happen in the cloud. You then run test and then an apply, and basically it goes and sees what you have in the cloud now and makes them match, like your model to what's actually in reality. Brings them back into alignment if they had gotten out of alignment. So if anyone had gone in and made a rogue VM and started handcrafting a fine bespoke server, we can wipe that out right away. make sure it doesn't interfere.
Slap the wrist.
Yeah, slap the wrist.
And fix it.
And fix it at the same, and actually heal it at the same time.
Mm.
Saltstack, on the other hand, has features I like around configuration management of the server. So for the application itself specifically, and then it can do orchestration and event-based orchestration. So I can, as a developer, have access to the Saltmaster to release code to the servers, but not necessarily install new applications onto the server. Okay. So I have orchestrations I can pre-configure for developers or admins to run common tasks against the server. For example, bring the production data from prod back to testing.
I see.
One command. Normally, that could be a whole lengthy list of scripts that someone's written into a wiki page someplace. We've now write it into a YAML file as a set of orchestrations. You can also do event-based orchestration, and I'll talk about that actually later in my talk this afternoon when I'm talking about deploying and automating with Saltstack.
So again, this comes back to not having anybody log into the machines to do anything. Mm-hmm. If you've got this salt command, you can run it, just takes care of it, and it does it the same way all the time.
Yep, exactly. Mm-hmm. But we have a bit of a chicken and egg problem. Mm. How do we get the Saltmaster up there first? So we want to be able to make sure everything is automated. Everything should be as push button as possible, and we shouldn't. I still don't want anyone to log into the AWS console and create a new VPC and VM for that Saltmaster. So what I recommend to people, and how we basically start up, is we write a little quick Python or shell bootstrap script that will, still with automation, still with a code we can basically code review and test and check in and revision. It will do all the bits and pieces of talking to the AWS API, creating the VPC, creating the subnet that the master will now sit in, create the EC2 instance, bootstrap the EC2 instance all the way up to being a Salt master. Like, for example, pull down the Salt states repository onto that machine. So it's ready to roll. And then at that point, an admin can now log into it and run the single commands to orchestrate. So with using basically Python and Bado3, the Bado3 library provided by Amazon, which is a Python library to bootstrap this whole process, it makes it very consistent. So we end up, if we want to make a new master in another region, you just point that at another region as an argument to the bootstrap script, and now we've got a master in that region instead of in the original region. So for things like disaster recovery. And then we orchestrate. You can see here we've got a couple example commands of running an orchestration. So if we wanted to deploy an environment, like the whole stack of VPCs, subnets, etc., we can now specify a specific environment like prod, or in this case, like test. So we run the salt run. It has a command called state.orchestrate. You write your orchestration. This is the bit we made here, the deploy environment. And that is a set of states and pillars and data that describe how to set up our environment. And then it builds it all out.
What's a pillar?
Pillar is data about the environment. So in our case, the states, I'll talk about this in my talk later today, but I get much more deeper into this there. But pillars are the data part of it. You can think of the deployment as like a template that's devoid of the data about what it's supposed to do. And the pillar fills in all the blanks saying, well, this is a production environment. You're going to use this range of IP addresses. You're going to use this set of AZs specifically. You're going to use these credentials for the databases. They're all production based values. When I switch over and use the test pillar environment, that's where I now get the alternate set of values that are for the test environment, but I'm using the exact, so you'll notice here I'm using the exact same orchestration, the exact same template to construct both these environments, but they're for different purposes and have different characteristics based on the pillar data.
I like it. I mean, knowing that you're recreating a test environment that really is the same as the production one, that's great.
It gives you a lot more confidence that things are going to work repeatedly over and over again, so you can fully automate this whole process. We may not even get to showing the AWS console at this point. Cool. One other thing I want to talk about with running Plone in the cloud is we want to make sure we keep our costs down. If you let AWS do it, it will eat all of your money. They're very good at that because these resources are not free, and we want to actually be able to control our costs. And there's some cool tools out there. One of the ones we've worked with quite a bit is Cloud Custodian. This is just a snippet of part of a policy, but basically with Cloud Custodian, you can write YAML policies around how you want things to act inside the cloud, and then either on a schedule or with using CloudTrail events, like API events happening inside the environment, it can now keep you in compliance. In our case, we want to spin down the test environment after business hours and on weekends. That immediately saves you like almost 40% off of the cost of running that environment. And so this Cloud Custodian policy this one is specifically for EC2, but you can run it against EC2 and the ELB and all the resources that are in that stack, and say that at 4 o'clock in this time zone, we're going to run look for the off-hour tags and run the stop action on all those items. So this runs in Lambda. You write the policies in YAML. We check them into our source code repository right alongside the code. And then anytime someone wants to adjust those policies, they adjust the policy, commit it, and then run Cloud Custodian to update the Lambda serverless code that's actually in the background doing these things. This one's using a schedule, so a rate of 1 hour, for example. You can do other things, like for example, if you wanted to make sure that your S3 buckets keys are always encrypted with a specific, maybe customer provided key, you can look for an event, an S3 event coming into Lambda, and then go and self-heal those keys and re-encrypt them to make them sure they're in compliance. So I recommend tools like this to people because it's going to help you. We are humans, and we're very good at making mistakes. And these are computers, and they're very good at fixing our mistakes as long as we tell them to. And so tools like Cloud Custodian are really good about that. So this one, in this case, we're using it to save money. You can also use it to stay in compliance. So if you have developers on the environment spinning up new EC2 instances, but they're using old AMI images that have old versions of software, you can actually prevent that, or you can warn them and then automatically terminate instances after like a predefined like workflow time.
Okay.
Yeah, it's pretty cool stuff. Sounds too easy, right? It was definitely bumpy. I mean, getting to this point, we started this early on when some of these tools were very brand new. For example, the EFS portion of that, where we store the blob storage, I think that tool had just coming out of beta or like developer preview from Amazon. And so my recommendation to you folks out there in the crowd, don't rely on Amazon tools that are just coming out of developer preview. They are still at very best beta. Even some of the ones that are released are still, and the issues we saw, for example, we're running EFS there was definitely performance issues. One of the things with a lot of Amazon services, the more you use of that service, typically the more IO and the faster and the more bandwidth you typically get with those services. So our blob storage was only probably a few hundred megabyte, maybe a couple hundred gigabyte at best. Unless you're running terabyte or more in EFS, which costs you some money, but if you're running that level, you'll start getting better performance because they start putting your data across more and more spindles behind the scenes. So more and more, I say spindles, it's probably SSDs. It's not, there's no one, I mean, they have spindles still, but basically they start distributing, because there's so much more data, they start distributing it across many more resources. And when they distribute it across many more resources, you get the advantage of all those additional IOPS. So the input-output operations now can start multiplying as you have more data in the system. And early on, it was slow to begin with, and even slower because we had less data. So blobs would be timing out, like getting into Plone. Yeah, it was definitely a little rough when it comes to that.
That's something you wouldn't think about.
No, and you just be like, oh, well, Amazon offers a shared NFS mount. I should be able to just use it, and it would just work as expected. But there are performance characteristics to all these various services that you have to pay attention to, and some of them now give you the opportunity to buy provisioned IOPS. So even if I have low amount of data, I can say I want to make sure I have at least this amount of performance. It costs obviously more, but now you can put the money where you want the value very specifically.
So that kind of that raises the question for me: how much more expensive do you expect an Amazon deployment of a system like that to be than buying your own server, trying to provision your own server, and then do all your maintenance?
I expect it to be less. I think the Amazon costs are going to be less. I mean, if you look alone, if you were to buy a server like this to host an application, first of all, you're going to have to buy at least two and have them in 2 different data centers.
Right.
So you have the cost of multiple data centers, you have the cost of multiple connections. A lot of people don't think about the power, the cooling, the internet connectivity, the redundancy at each location's internet connectivity. There are a whole bunch of moving pieces under the covers. And then you got to have the people who actually have the knowledge on staff to be able to maintain BGP and network routing and VLANs and VXLANs, and then that's just the networking piece. Then they got to have people who understand the data center and the cooling and running the electricity and all the power bits. Another piece. Then you got to have the sysadmins and the network engineers, and like there's so many resources you would have to get this level of resiliency and performance on a site like this. And for example, in our deployment here, the EC2 instances that are running in AZ1 and 2, these are both M2 small. They're very, very small instances. They probably, with a reserved instance contract, no upfront, I think we're paying $10 to $15 a month
Really?
each for those servers. But the site performs as if it's hosted by
it's nice. It's
a giant
fast.
piece of infrastructure, mostly because of CloudFront. The reason we have these like this is so that we do have resiliency for people who are editing the site. I mean, typically the only people who ever hit the connections on those actual EC2 instances are the people editing the site. So the resiliency is really for the editors at this point, because it can be hosted mostly static via a CloudFront.
That's remarkably inexpensive because, you know, I come from Cloudflare and Linode, and a Linode would be $10, $20 a month easily.
Now the RDS is pricey. I mean, you are paying for basically the same cost of like an EC2 instance plus the management of whatever database you're putting on there. This is probably another $15, $20 a month for the database service. And if you run it multi-AZ, you take it times 2, because you're basically running one in each availability zone as well. And then you have full high availability. If a whole AZ drops off the earth, our site stays alive.
But so again, going back to the cost equation, it's not a simple one-to-one, because what you're able to do with Amazon deployments is there are things that you couldn't really imagine doing if you were doing it yourself.
Correct.
So that's okay.
Right. I mean, managing and running an EFS server or an NFS v4. I don't know if you've ever tried to set up NFS v4.
It's been a while.
It's hard. NFS v3 was very easy. NFS v4 added a lot of complexity there. So they take a lot of that complexity out of the way for you, which I think is a big benefit to running even what feels like a monolithic application like Plone in a cloud native way on Amazon. Has worked out very well for us. So yes, does sound easy. Definitely have some trickiness. Now, you still have to pick like what operating system you want to put onto your EC2 instances. And so kind of as we round this out, we're almost done here on time. But I do want to repeat a little bit of the ZenoPython. I'm a big fan of ZenoPython. All of you people out there in the audience, I highly recommend that you actually go and get the ZenoPython and do a import this from your computer, print that out, frame it in a very nice frame, put it on your wall in your bathroom, so as you brush your teeth every day, you can just read the ZenoPython. You'll become a much better person in general if you do that. But one of the items in the ZenoPython, one of the tenets is there should be one, and preferably only one, obvious way to do it. Although it may not be obvious at first unless you're Dutch. I'm not Dutch, so it wasn't very obvious to us the correct way to do this when we first started. But basically, when we started on this journey, it was a brand new deployment. I was like, this will give us an excellent opportunity to explore Amazon Linux. If we're running Amazon Linux EC2 instances on AWS, I would assume we would get better performance. They hopefully have tuned it, run all the bugs through, tested it really well. Well, we did deploy with Amazon Linux, only to find out that basically Amazon Linux is an old version of CentOS. And it sure is tuned for maybe their storage nodes and all those other kind of things, but that actually didn't matter. What really mattered to us was going to be availability of modern packages. In this case, the version of HA proxy was too old to support a specific function we were using in the environment. All right, let's get a newer version of CentOS. So we went to CentOS 7, this is at the time, this is a couple years ago, only to find that the versions of WV and one of the other tools we use instead of Plone for document conversion, too old, didn't work with Plone. All right, fine. So I'm a huge fan of FreeBSD, and I was trying not to exert my opinions.
I was thinking Ubuntu, right?
On the okay. I do run Ubuntu on my laptop, but don't tell the BSD people. I run BSD everywhere else.
Those Canadians.
Yeah, so we ended up actually refactoring back to FreeBSD because FreeBSD does have a modern packaging system that is kept very up to date. So we had modern HA proxy, modern WV, and all the libraries and dependencies we had for Plone are actually really readily available on FreeBSD. So in the end, refactored for FreeBSD, but it took us 3 rounds. I think we may have actually put Ubuntu in there at one point in time because I was like, come on, certainly.
Very nice.
Certainly. Well, the reason why we did this, you could add third-party package repositories to one of these operating systems, but then you're now maintaining or hoping that whoever manages that third-party random repo you added to your system is maintaining their repo, which doesn't happen.
Right.
I only wanted vendor provided or provided by the creator of that operating system's repos only in the system. So that way it can be kept up to date very, very easily. So you're always just either apt update or yum upgrade, or in the case of FreeBSD upgrade, so that by default those will upgrade all the packages as they are maintained by the people on the operating system tooling.
Mm-hmm.
And luckily, I see Caleb's getting ready to give me the boot there because we are 1 minute away. I do want to say thank you all for joining us today on running Plone in the AWS cloud. I want to thank Kim for joining me today as well.
Thank you.
I think it's been a real fun presentation, and I will hand it back unless there's any questions. I haven't seen any questions in the Slack room pop up.
In the Zoom Q&A, there is one question.
Oh, okay. Let me. Oh, you sure? Certainly, there sure is. Let's look at that. Have you done any work for backup providers, for backup cloud providers, and getting your workflow to work on Azure, Google, and others? I have not. So we primarily deploy to AWS. We do use some DigitalOcean here and there. I have lots of thoughts and ideas on that, and that's one of the reasons why we use Terraform and Saltstack and not CloudFormation on AWS, is so we can actually keep this cross-platform. So I hope that helps you with your answer. I'm happy to talk about it later. Actually, hit me up during my Saltstack talk this afternoon, and I can go over that in a little more detail on what I would do there. I answered that live. Look at that.
Ooh. So I had a question on those operating system changes.
Yes.
Was that complicated to deploy?
No, because each time we did it, all we had to do was modify what AMI image we would pull in to build that EC2 instance. Now, because we maintain our salt states typically with the cross-platform ability, no matter which state we're running against what operating system, if it's going to be Ubuntu or CentOS or FreeBSD, we have mappings for the correct package names for the same dependencies. So in one it may be, libjpeg-dev, and one it may be jpeg devel,
right?
Or you kind of know where I'm going with that. But we basically Saltstack allows me to maintain cross-platform ability to do that. So change out the AMI, install a different OS. When it boots up, it sees, oh, you're Red Hat instead of CentOS, or you're Red Hat, or instead of Ubuntu or whatever, and goes.
Wow.
Cool.
Yeah.
Thank you, Caleb. I'll give it back to you.